Hello guys, welcome back to the universe of Tech Hub. In this tutorial, we will learn about Dijkstra algorithm. Have you ever wondered how Google Maps finds shortest route between two places? It's using a algorithms like Dijkstra algorithm. In today's video, I will explain Dijkstra algorithm in a simple terms and show you how it's used in everything from navigate to computer networks. First, we need to understand what is Dijkstra algorithm. Dijkstra algorithm means a graph consists of a nodes or vertices and edges connecting them. Imagine a city map where each intersection is a node and the roads between them are edges. These basically what is Dijkstra algorithm like that. In technical term, Dijkstra's algorithm is a graph search algorithm that solves the single source shortest path problem for a graph with non-negative edge weights, no negative edge weights. It finds the shortest path from a starting node or vertex to all other nodes in the graph. This Dijkstra's algorithm is a well-known as algorithm in a computer science and graph theory used to find the shortest path from a starting node and also called as a source node to all other nodes in weighted graph. The graph can be redirected or undirected and the edge weights must be non-negative. The algorithm works by iteratively selecting the node with the smallest known distance from the source and updating the distance to its neighboring nodes. It guarantees finding the shortest paths in a graph with non-negative weights. Why is this cross algorithm used? Next, this cross algorithm used to find the shortest path and network routing and graph traversal. These are all the why we need to use this cross algorithm and commonly used in shortest path finding, network routing, and graph traversal. In shortest path finding in navigation systems such as GPS route planning like that and network routing for data transmission in a communication system and in the graph coming into the graph traversal in various applications like web crawling traffic flow optimization and game AI. These are all the where is this graph algorithm used. The key advantage is that finds the optimum path least computational cost in a graph with non-negative weights. These are all the where we need to use this grass and why is this grass algorithm used like that. Next, we move on to the applications of this grass algorithm. This grass algorithm, the application of this grass algorithm, GPS navigation system. It helps in finding the shortest route between two locations. Next, computer networks it is used in routing protocols, RIP, to find the best path for data packets like that and flight travel path used by airlines and travel agencies to find the shortest travel path airlines networks like that. And next we are using in game development in AI for path finding in gaps maps or grids like that and also used in telecommunications for optimal data transfer routes in a networks. Then also another one is social networks to find the shortest connection between two people or LinkedIn or Facebook like that. Next one is how this cross algorithm works and these are all the algorithm steps. First we need to initialize set the distance to the starting node to 0 and all other nodes to infinity. Next one is create a priority queue and add the starting node. These are all the initialization steps. And next we move on to the process the queue. While the queue is not empty, extract the node with the smallest distance. Let's call it current node. For each number of the current node, calculate the tentative distance from the start node to the neighbor. If this distance is less than the previously recorded distance, then update it. These are all the process the queue. Next, mark as visited. Mark the current node as visited. Remove it from the queue. This is the mark as visited part. Next, repeat and continue until all the nodes have been processed or the queue is empty. This is the repeat process. Next, return the result. Return the shortest path distance from the starting node to all other nodes. This is the algorithm for Dijkstra's algorithm. Next, I am taking an example to implement how Dijkstra's algorithm works. Let's take an example. In Dijkstra's algorithm, single source shortest path for a graph G is equal to V of V comma E. Means V means vertex, E means edges. Update the distance to neighboring nodes only when a shorter path is found. Let's take one graph. These are all the nodes B. A and B weight, so the A and B weight is 2. B and C weight is 4. And C D to C is 3. This is 3. And D to E is 1. A to D is 1. And B to D is 7. This is the highest weight is 7. This is my graph. This is my graph. First, I write some given. To B is 2. And A to D is A to D is 1. Next, D to C is D to C is equals to 3. Next, B to D. B to D is 7. Next, B to C. B to C. B to C is 4. D to E. D to E is equals to 1. This is my given in this graph. This is the given. Next, what I need to do is, first step is initialization step. I am taking small table. First one is nodes. The second one is distance. The nodes are A, B, then C. Next one is D. Next one is E. These are the nodes. First we need to initialize A is 0. Next all are infinity. This is the initialization. Next, the priority queue is of this is the now priority queue. The step 2 is the process A. The step 2. This is the step 2. Process A. The distance is equals to 0. Process A, distance is equal to 0. The steps 2. The current node is A. The distance 0. Neighbors of A is D and B are the neighbors of A. So we need to check A to B weights are 2 and A to D weights is 1. So the new distance is A to B is A to A to B is distance plus A to B distance weight is 2. So 2 update B's distance 2. Update B distances 2 right now. A to D new distance. A to D is equals to new distance. This is our new distance, right? 0 plus A to D distance is 1. So the updated distance is 1. The new distance is 1. Update the D's distance. The D's distance is 1. Updated distances. The priority queue is of 1 and B of 2. This is our priority queue. Next, step 3. In the step 3 process, we D. Why we need to process D? So, in the neighbors of A to B, A is A to B and A to D. This was the smallest weight. The D to A to D is the smallest weight. So, I need to take process D. This is equals to 1. The D distance is equals to 1. Right? We need to calculate D's neighbors. The D neighbors A and E. A is already visited, so E. We need to check E. New distance of D to E is 1. D to E distance is 1 plus 1. The distance is equal to 1 plus D to E distance is equal to 1. 1 plus 1 is equals to 2. We need to update D's D's neighbors are A, E and C. A is already visited. C and E is now we need to visit. D to C is 3. New distance is equals to D to C. So D to C distance is 3. 3 plus 1 equals to 4. So update C's distance. Distance to 4. We need to update C's distance. In place of infinity, we need to write 4. This is the updated new distance. And what step 3? Next, these are all the updated distance. A is equal to 0, B is equal to 2, C is equal to 4, D is equals to 1, and E is equals to 2. The priority queue is the priority queue is E of 2, comma E of 2 and C of 4. This step 4 is process B. Process B. First, B weights are 2, E weights are 2, C weights are 4. First, we need to process B. Next, we need to process E. Next, we need to process C. First, we need to process B. What is B distance is equals to B distance. B distance is equals to 2. The neighbors of B's are A, C, and D. Already we are visited A and B to C is 4. Then neighbors of B to C. The B new distance. The neighbors of B to C is 4 plus distance 2. The weights are 6. Since 6 is greater than 4, yes. No updates to C. No calculate B to D. New distance to D is 7. 7 plus 2 is equals to 9. So, since 9 is greater than 1, so no update. The weights are 1. So, new distance B 9 is greater than 1. So, no update. 9 is greater than 1. Yeah. Yes. So, no update. No update to D. 6 is greater than 4. Right. So, no update to C. Next, distance array remains unchanged. because there is no update in process B. So the priority queue is E of 2, comma C of 4. This is my priority queue. The step 5 is process E. This is the step 5. Distance of E is 2, 2, right? Of E is equals to 2. Now, what we need to do is we need to check in the E neighbors. The E neighbors are E has no unvisited neighbors. So distance array remains unchanged. Priority queue is no unvisited neighbors. No unvisited neighbors. No unvisited neighbor. The priority queue is CO4. Next, we perform step 6. Is C. So we need to process C. The current node distance is the distance is equal to current node distance is 4. C neighbors are C has no unvisited neighbors. The C has no unvisited. The distance array remains unchanged. The priority queue is empty. Now the priority queue is empty. Right. The final output is some final output. This is our final output. The new distance is 0. The new distance of B is 2. The new distance of C is 4. The new distance of D is 1. The new distance of E is 2. This is the final output. The main aim of Dijkstra's algorithm is to find the shortest path from a given source node to every other node in a graph. This is our final output implementation part. We need to import HPQ. Purpose of in the purpose of import HPQ is which provides an efficient implementation of priority queue. Like minimum heap, a priority queue helps in efficiently retrieving the node with the smallest distance at each step of the algorithm. That's why we need to import HPQ. Next, we need to define Dijkstra's graph and start at the parameters. I need to take graph and start at the parameters. So this defines the discourse function that takes two parameters, the graph representation as an adjacency list where each node has its neighbors and their corresponding edge weights. The starting node from which we need to calculate the shortest paths to all other nodes. That's why I need to take graph and start at the parameter. Next, need to define distance of start equals to float of for node and graph. The purpose of initialization as a dictionary dist where each key represents a node in the graph and the value represents the current shortest distance from the starting node start to the node. We start with the assumption that all the nodes are infinitely far away from the start node except for the starting node itself. Next, list start is equals to 0. We need to initialize 0. The purpose of we need to initialize 0, this sets the distance to the start node as 0. As the shortest path from the starting node to itself is always 0. So that's why we need to initialize 0. Next, we need to initialize PQ is equals to comma start. The purpose of this is they initialize the priority queue PQ with triple 0 comma start, where 0 is the distance to the start node already set to 0. The start is the starting node. The next we need to use while PQ. The purpose of while PQ is this begins the main loop of the algorithm. The loop runs as long as there are elements in the priority queue PQ. The distance from the priority queue. If the queue becomes empty, all the nodes have been processed. The next, the current is the current dist comma the current node. The current node is equals to heap pq dot heap of pq. This line pops removes the node which is the smallest distance from the priority queue. It returns a tuple like current dist and current node. The current dist is the distance of the current node from the starting node. The current node is the nodes with the smallest distance. The main idea of Dijkstra's algorithm is to explore the node with the smallest down the distance first. The priority queue ensures that we always process the node with the smallest tentative distance. So that is why we need to write this line. Next, if if current if current dist comma the current node is equals to epq dot heap heap of pq. This the purpose of why we need to write this line means for if current dist is greater than dist of current node. This is a God class to check if the current node has already been processed with a shorter distance. If the current dist is greater than the recorded distance in dist current node, it means that a shorter path is to this node has already been found and processed. Therefore, we skip processing this node again by using continue. This ensures that we don't process nodes that have already been processed with a similar distance. So that is the reason why we need to use if. Next, for neighbors, neighbor, neighbor weight in graph is equals to current node dot items. So the purpose of for neighbor comma weight in graph current node dot items is this iterates over the neighbors of the current node in the graph dictionary. The values associated with each node is another dictionary that contains its neighboring nodes and the weights of the edges connecting them. The loop gets each neighbor and its corresponding weight, the edges weight. The Dijkstra's algorithms updates the distance to the neighboring nodes of the current node. So we need to explore each of its neighbors. So that is the reason we need to use for loop. Next, distance is equal to current distance plus weight. We need to calculate a distance, new distance. Distance is equals to current, the current distance plus weight. The purpose of calculate the tentative distance to the neighbor distance to a neighbor is the sum of the current node's distance. The current distance and the weight of the edge connecting the current node to the neighbor weight. This is the purpose. Why we need to use the distance is equal to current distance weight. This calculations. This is the key steps in Dijkstra's algorithm where we calculate the potential new distance to a neighbor node. If this new distance is smaller than the current node distance, we update it. So that is the reasons using this. Next, if if distance is less than dist dist of neighbor is equal to dist neighbor is equals to distance. This check if the newly calculated distance to a neighbor distance is smaller than the current distance stored in this neighbor. If it is, we we update the this neighbors with the new smaller value. The Dijkstra algorithm is all about relaxing edges, meaning we only update the distance to a node if we find the shorter path. This ensures that we always store the shorter noun distance to each node. This is the reason why we need to use the next EPQ. EPQ dot heap push of the PQ, comma distance, comma neighbor. Purpose of EPQ dot heap push. After updating the distance, this line pushes the updated node to the neighbor. In previous example, I need to shows everything how it works. The updated node neighbors and its new distance into the priority queue, the PQ. This ensures that the neighbor will be processed in the future with the correct shorter distance. The priority queue helps efficiently select the next node with the smallest tentative distance. By adding the updated neighbors to the queue, we ensure it will be processed at the right time. Next, we need to return the dist. That's it. After the priority queue is empty and all the nodes have been processed, the function returns the means dictionary, which contains the shortest distance from the starting node to all other nodes in the graph. This is the final output of the algorithm. It provides the shorter path distance from the starting node to every other nodes in the graphs. Next, we need to represent the graphs in adjacency list. So I need to take graph. Graph is equals to, in graph we represent using a curly brackets. My graph, this I am taking this graph. The A neighbors are B and C. A to B weights are 1 and A to C weights are 4 and B to A weights are 1. B neighbors are A, C, D. B to A weights are 1 and B to C weights is 2 and B to D weights is 5 and C neighbors are A, B, D. C to A weights is 4. C to B weights is 2. C to D weights is 1. This is C neighbors. Next, D neighbors are B, D to B and D to C. D to B weights is 5, D to C weights is 1. This is the graph. This represents the graph. Next, puts of the updated weights of the A to A is 0, A to B is 1, A to C is 3, A to D is 4. This is the updated distances or weights. This is the updated weights. This is all about Dijkstra's algorithm. If you like this video, please don't forget to subscribe, like and share and comment in this video.